My name is Govind Radhakrishnan. I am a member of technical staff here at CMC Microsystems. I'll be presenting the first half of the slides, and Viper would be taking it from there. So a brief background on CMC Microsystems. CMC provides services to simplify access and reduce cost to advanced technologies. We are focused on microelectronics, photonics, MEMS, nanofabrication, AI, and machine learning. We also look into quantum technologies. So basically, we provide academic and industrial support. CMC is a not-for-profit organization founded in 1984. We manage the Canadian National Design Network, and we provide infrastructures for innovation. CMC, we primarily focus on three divisions. Basically, first, CAD. We look into state-of-the-art softwares for successfully designing your chips. So basically look into computer-aided design tools and environments, a secured distributed private cloud for hosting. We also provide user guides, process design kits, application notes, training materials. On the fab side, we work on prototypes, basically multi-project wafer services through our global supply chain. Basically, we focus into microelectronics down to 12 nanometers, and we look into silicon photonics, MEMS, and nanofabrication. We also provide expert assistance for first-time right designs. And we also offer packaging and assembly services. In the lab, we look into providing platform for test equipment loans for short-term needs. We also provide technical contract services for quantum coding, constructing neural research networks, and we also have international partnerships for unique needs. For multi-project wafer services, these are some of the companies we work with in order to handle the multi-project wafers. So some of you have seen these companies already if you have gone to one of our MPW services. Packaging and assembly, prototyping access, support, and CMC engineering expertise is offered for off-the-shelf packaging, wire bonding, and encapsulation. We also provide options for die bumping, flip chip, photonics packaging. We provide assistance for laser-assisted cleaving, die on board, and die stacking. These are some of the companies we work with: CMMC, QP Technologies, and Celestia. At CMC, we work on advanced technologies across all strategic sectors. These are some of our success stories with our customers. If you want to know more about these success stories, please feel free to browse at www.cmc.ca/success stories. Our global partners, we have a worldwide industry supply chain. Mostly we are in Canada, but we are working with Europe, Asia, Australia, and USA. So the fab services are spread across the globe. Now, let's look into the objectives of this presentation. After this presentation, ideally, the designer should be aware of the process to choose the packaging option. Some of the design considerations you need to look into for wire bonding. The user should be getting familiarized with the packaging request process and the timeline. And also, Viber would be discussing on additional services available through Foundry Packaging House. So basically, circuit on board packaging, partial encapsulation, overmolding, subdicing, those kind of stuff. Before we start the presentation, let me give a brief glossary of terminologies that's used in this presentation. Core circuitry is basically the circuit under test. It includes the peripheral circuitry, clocking, power level shifting circuits, etc. The I/O blocks are the input-output interface between the core circuit and the bond pad. Now, bond pads are terminals in the die that connects to the package. So all the core circuitry, I/O block, and the bond pad lies within the die. Now, the pad frame is a term that's used for calling the bond pad and I/O blocks together. So it's composed of I/O block and bond pad arrays. The bonding wire is a metal wire connecting bond pad to the packaging lead frame. A lead finger or a bond finger is a metal pad structure on the package where bonding wires are connected. Lead frame is a metal structure inside a package that carries signals. And RFI is a request for implementation. Now let's go through the project flow. Generally, we start like a student in an academic environment. They start with a design idea, and you want to implement that idea on silicon. So first, what we do is you come up with a test methodology to find out what are the input and output signals within your test chip, and what are the test signals you need to access. So once that idea is clear, you kind of know how much pads are needed, how many inputs are there, outputs are there, how many pads are needed, what's the core circuitry involved. Once that is done, you go forward with step 3, which is a preliminary floor plan. So what you do is you place the core circuitry and populate the pad frame around the core circuitry. Once that looks good, we go forward with the design implementation and the verification. So you might be familiar with that. We basically go from schematic to layout to DRC, LVS, post layout extraction, verification, those steps. Once the designer is confident with the design, they go for submitting the design to us. We do the tape out to the fabrication facility, and the design is fabricated. Once the design is fabricated, the designs are shipped to the packaging facility, and the packaging is done, and finally you receive the package dies. So in this whole flow, where do we consider packaging options? I would highly recommend you start considering the packaging options right in the step 2, which is a test methodology. You kind of have a why you need to do that is because once your die is already implemented, you cannot actually change the die information, right? So you might have to choose a package that's based on the die, and maybe that package may not be available to you. Second thing, your design has got certain constraints. So suppose say you have a design that's a high-speed design, you might want to look into the electrical characteristics of the package itself so that the signals can be handled properly. So basically, package is a window through which you can view all the signals. And I would highly recommend you start looking into the packaging option in the testing methodology phase. Now, when do you consider the packaging criterion? So we should consider the packaging option right when you submit the design to us. So here you see a typical IC flow. So we have the client submitting the design GDS via SFTP to CMC. At this moment, you should be able to tell us roughly what's the package type you're looking for and the quantity you're looking for. This basically derives from the testing methodology you are using to test your circuit. Once that information is known, CMC can raise an invoice for you, and the designs are shipped. The GDS is shipped to the fab along with this packaging information. Now, once the fab fabricates the dies, it goes into the packaging environment, and they do the packaging for you. The package dies then comes to the client. So if you're looking for packaging through QuickPack QP technologies, you have some time before you can submit the bonding diagram. Basically, you can submit the bonding diagram while the die is in the fab. But if you're looking for packaging through CMP, I would recommend submitting the packaging information right when the GDS is submitted. So this sort of tells you when you need to consider packaging and what information you need to submit. Now, I said consider packaging options. What do you consider when I mean like consider packaging options? First is we do this packaging consideration on 2 phases. One is the pre-design phase, where when you're in the testing methodology and the preliminary floor plan stage, you can look into what are the number of pins you need, Based on that, you can choose a packaging type. You might also want to look into power, speed, and heat considerations, and based on which you need to choose a package. So I would recommend highly to look into the CMC packaging options. You can go into www.cmc.ca/package assembly, where we have a list of packages that are readily available. Please also check in on our webpage for special packaging discounts that's available from CMC. These are offered mainly for newer packaging technologies like flip chip. Additionally, you can also look into QP provided packages. Go to QP Technologies, and they offer technical specifications and like diagrams for the package. So this kind of gives you an early information on what package you need. But once you go into the design phase, you can also, you'll be looking into the layout aspect ratio of your core circuitry. You might want to look into the pad frame versus lead frame selection, bonding wire length considerations, package design, co-simulation, etc. Now, a preliminary floor planning stage. So this is just a case scenario in a typical design flow. What you do is we have, like you guys, designer would have a circuit and sub layout, and what would they do is like they add all the sub module layouts together and kind of estimate the core area occupied. Now, once that area is known, you also know the number of pads you need for your design. So you place a rough pad frame across around the core with an estimate, like a number of pads needed, and based on the pad size, you can get those information from your design rule manual of the particular PDK. So during placement, the main goal is to efficiently occupy the area allocated with the core circuits and the pad frame. Now, in an ideal scenario, your core circuit will completely occupy the area within your pad frame, but most likely you would encounter two scenarios like this. One is a pad limited scenario where you have a lot more number of pads and the core circuitry is small. So in such case, there is a lot of unoccupied area around the core within the pad frame. So this is not good because you're not effectively utilizing all the area. The second option scenario would be you have a big core circuitry, but the pad frames are like limited. So you can see that there is unoccupied area here on the edges of the line. So this is also not a good scenario. So a proper selection of pad frame can help you utilize the area allocated for you. So how do you choose a pad frame based on this? So suppose, say, the design is like, the floor plan is like core limited. So we can go for something called an inline pad frame option, where you place the bond pads inline to the IO pads. This is a very common scenario where the core area is too big. So in this case, the bond pads and IO pads are aligned, and if there is gap between these bond pads, you can actually put filler cells in between, so that establishes a powering. In case of a moderately pad limited scenario, you can go for something called a staggered pad frame option, where you distribute the bond pads in a staggered fashion. So in this case, you can literally pack twice the number of bond pads here. And IO pads can be abutted together. So it's a very efficient way of arranging the pads. Now, if for some reason, if your design is still pad limited, so you have a lot more pads, something you can consider is the flip chip option, where you actually distribute the bond pads within the core area. And we are using the redistribution layer, that's the topmost layer in your kit, and connect the top metal to the bond pad. So flip chip, there are different flavors of flip chip. You can distribute the bond pads around the periphery, or you can distribute across the core area, or you can choose an option that's somewhere in between. So let's say if you have the layout that's done for a wire bonding scenario, and you want to try a flip chip option. So this C scenario would be good for that. So literally you can take the wires from, use the RDL layer to route the wire bonds to the bumps here for flip chip. So That gives you a summary of how to choose a pad frame. Let's look at a suitable lead frame for the package. So based on the pad frame chosen, you can choose either a single tier, double tier, or a flip chip based lead frame. Single tier is suitable for inline pad frames. So there is no complications here. It's just a one-on-one mapping from the bond pads to the bond fingers. A common example is CQFP80. Another example is double tier lead frame that's suitable for staggered pad frames. So when the bond pads are staggered, it's so tightly packed, you might want to consider 2 rows in the lead frame. So this is something called multi-deck wire bonding. I can show you a picture later that's having this kind of wire bonding. The third option is flip chip. So here what you do is you place the bump die is attached to the carrier, and then the carrier then connects to the package. We provide an underfill that's added to the fill area between the carrier and the die. So these are some of the lead frame topologies you can derive from the pad frame topology chosen. So that's the whole summary of how do you choose a package based on your number of pads and core area. Now let's look into the bonding wire design considerations. So in an ideal scenario, we need to do a packaging aware design. The key goal is to utilize the cavity space and bond fingers in the package. At the same time, you want to minimize the wire bond length. So here I show some typical examples. So case A, you can see that the pad frame, it's only on 2 sides of the rectangle. This side and this side is not utilized. So it's not an optimal pad frame. And you can see the core is more rectangular. If you look into the packaging options, you can see that most of the cavity is square. So this die wouldn't occupy the cavity, in an optimal manner. So what you can do is case B, we can distribute the pad frame equally on, or try to be more uniform across all 4 sides. So you can use that and spread the bond pads more uniformly. But again, the case B, the core is not optimal, like it's not occupying the cavity space optimally. So case C would be the ideal consideration. It's optimized in terms of pad frame as well as core area distribution. Now this guideline does not apply if the core aspect ratio is part of the design specification. Like for instance, suppose you're designing something that would inherently be a rectangle, then this won't apply. This is just a guideline as to guide you into making the die suited more towards the package you're choosing. Now let's look at the bonding wire length. That's one of the design consideration. The longer the bonding wires, that increases the parasitics, RLC. So it's always good to minimize its length. There is also a limit to the maximum length a bond wire can be. It's less than approximately 6 millimeters. Beyond this, the wire droops and breaks. There are other options like interposers that can be added for longer bonding wire lengths, but this is expensive. So some of the recommended ways to reduce bonding wire length is to place the bond pads on the periphery of the die, choose a package with the smaller cavity size that fits the die, and another option is offcenter the die to minimize a specific group of bond wires. So now let's look into bonding wire diameter. Higher thickness of the wire reduces R and increases C. So that's suitable for higher current driving and power supply lines. The thickness also depends on the bond pad size. That's something the packaging company provides. So for example, a 1.2 mil gold bonding wire, the pad size should be greater than 65 micrometer. Now, if your chip works at a very high speed, such as RF, then you need to consider proper driving and you need to consider the parasitics involved in the wire bond. For that, please contact fab@cmc.ca for more information on electrical parameters. We will be able to provide the RLC values for a given wire length and diameter. Now, for sometimes you want to get more information on the top metal layer and redistribution layer electrical characteristics. So for that, you need to look into the PDK design rule manual. So that's kind of like the design considerations. Let's look into the packaging request process itself. So these are for users in MPW runs or if you're needing any standalone packaging. So the information to provide for the packaging request, you need to provide the design name. We have a standard methodology like ITT, UU, XXX, where I is for implementation, TT is the technology code, UU is the university code, and XXX is the design code. You need to provide the CMC run code. You need to provide the number of dies to be assembled, the pad dimensions, which include the pitch, the pad opening, and the pad dimension itself. You need to provide the exact die size, the total number of pads, the number of pads that are connected, and also the wire bonding diagram, accordance with the packaging type. So for the wire bonding diagram, we should be able to provide you a template as shown here, in which you can place the die and draw the wire bonding diagram. And we can send the image of that diagram to us for the processing the packaging request. Now, this is an example for a bonding diagram. So a bonding diagram should have packaging pins, pin numbers. It should have a die outline, orientation, and the logo of the die. And the drawing should be to scale so that we can estimate how congested the wires are. So this is an example. On the left side, you see a die outline. And the right side, this is a zoomed in picture where you see the core design and where the wire bonds, the wires are connected to the bond pad. Now, as you know, like when you draw a wire bonding diagram, it looks like this on the top view, but in actuality, side view, this looks like that. And if you're going for something called a multi-tier or double tier wire bonding, the picture below shows an example. So you can see how complicated it can get when you go multi-tier wire bonding. So you need to follow some guidelines so that there won't be any short circuits involved and you get better yield out of this wire bonding packaging. So some of the common mistakes to avoid while providing bonding diagram is one, no crossing of bond wires. This will result in a short circuit there. The bond wires should not be too close in the bond pad size. The bonding wire should not be too close on the bond finger side as well. There's length consideration, like if the length is more than say 6 millimeter, that's a length violation. So the wire basically droops and breaks. There is an angle restriction. You can't go beyond a certain wide angle. And there is pitch violation. So basically this happens when the bond pads are distributed non-uniformly and the pitch keeps on varying. So this error can happen. So these are some of the common mistakes you can avoid and in the wire bonding diagram. Now, how do you provide pad dimensions? So for pad dimensions, below is a diagram for pad array. You need to provide the pad pitch, bond pad dimensions, and bond pad opening. So this is just a sample diagram you can use for your packaging request. So with that, I will transfer the control to Vaibhav. He'll be talking about additional services available through our packaging house. Thank you.
Thank you, Govind. Good afternoon, everyone. I am Vaibhav. I am a part of Microelectronics team at CMC. So apart from the standard wire bonding services that we offer through our packaging suppliers, there are some additional services that are available through the packaging house and the foundry as well. So the first one that you can offer is like a package encapsulation. We are seeing that there is a growing demand for some of the applications which require the chips to work in harsh environments. Sometimes wet processing of some samples are required and you need to immerse the chip into some liquid solution. For that kind of applications, we can look into partial encapsulation of package where we can just leave a selective opening on top of your die and encapsulate rest of the chip and the package wire bonds, everything. So in the package encapsulation, the epoxy that's used by our packaging house, QuickPack or QP Technologies, is Hysol FP4323. The things to notice here that this epoxy is having is reportedly having excellent moisture resistance and excellent chemical resistant characteristics. So ideal for testing out some samples if someone is working in like biological research or testing out chemical samples, etc. So what do we need in order to request an encapsulation request from the packaging house? We will need the package and the die information. You will need to provide the package drawing number and the die information in terms of what is the die size, what material it is, if it is a silicon die or a gallium arsenide 3-5 die, something, the bonding pattern that the package and chip is having. And then we need to highlight how do we want the encapsulation job to be done. If it is full encapsulation, it's relatively easy. But for partial encapsulations where we want a selective window, we need to specify certain dimensions in the bonding pattern with respect to some key features on the design or with respect to the die boundaries. If you can also, when making a request to CMC, if the designer can specify the purpose of the request, like what application he's targeting, it becomes helpful for us to make any recommendations. So an example for packaging encapsulation drawing that we accept is given here. So here we have a package which is like PGA 69 package, and then there is a die at the center. When we order the partial encapsulation, we will need the critical dimensions given as A, B, C, D. A is the width of the opening that you want to create on your die. B is the height of the opening, and C and D are representing the critical distances from the edge of die horizontally and vertically. So what the packaging house will do is packaging house will fill in the epoxy in all the area that is shaded gray here, and the area within the red window, it will be left open for any sample testing. So in this way, the wire bonds and some of the die area can be protected against the samples which are being tested on the chip. The next thing that we can offer is like a chip on board packaging. This is growing in demand. The chip on board packaging offers flexibility to the designer in terms of optimal use of bond pads, design area. They can also do their custom substrates in order to bond their chips. The flexibility to move chip around on the PCB, which is bounded in case of packages, is not here. So that the designer can design a chip in such a way that he can try and reduce parasitics on some of the wire bonds and try to keep shorter connections from the PCB to the die. These can also be done on flexible PCBs, so the potential to work in flexible electronics. Multiple chips can be packaged on a single PCB. That's why like multi-chip integration is possible. The only thing to remember when ordering a COB job is is the finishing of the PCB, the metal finishing of the PCB. Generally, the PCBs will come in two different finishings, and ENIG and ENEPIG, like electroless nickel, electroless palladium, immersion gold. This finishing here, ENEPIG, this one is recommended from the packaging house. For the other finishing, for any other type of finishing, the wire bonds may not be bondable on the PCB. So this is an essential thing to remember. Even when we are going for the ENEPIG plating finish, the thickness of the layers should be specified to the PCB house where you are trying to design your PCB. We generally do these processes through QP technologies, and here is a summary of what QP is expecting for different layers of nickel, palladium, and gold. So these are the minimum critical thicknesses. So if certain PCB house is having not able to meet these requirements, please send an email to CMC and we can look into that special request. Even for chip on board requests, we will be able to handle the encapsulation requests. There are the full encapsulation, partial encapsulation, and special lead and frame arrangements are available when working on chip on board type of packaging. The next thing will be if someone wants to design multiple chips on a single die and wants to have them subsidized later after probe testing or anything, it is possible. The key important things to remember here are each design that you would like to subdice later must have a seal ring of its own. Seal ring is a structure that protects the die from mechanical damages in the process of dicing. The seal ring is generally provided by the foundry. So the recommended option is to use foundry provided seal rings when using it around your design. You can do custom seal rings, but make sure that all the design layers specified in the design manual for the seal ring design are present in the given seal ring, custom seal ring structure. The next thing to remember is if you are having multiple designs on a single die, please have a minimum distance required to run the dicing saw through the designs called a scribe lane. The typical scribe lane distance given by foundry or packaging house is in the range of 50 to 150 micrometer. CMC usually recommends keeping it close to 150 micrometer. The next thing is if you have foundries, they have certain density requirements to meet in order to fabricate your dies. So it is possible that you may have to fill in the scribe lane region as well, but make sure that you are doing low density fills in the scribe lane region so that the dicing saw can run smoothly and it does not cause any damages to the chip. And the next thing would be to floor plan your multi-chip design well so that it can be diced into minimum number of cuts. Like for the given example, we will need to have 2 cuts to remove the 3 chips from this design. So yeah, like the cut 1 is horizontal one and cut 2 will be the vertical one, and then we can have the dies separated out. For the information that we need to provide to the packaging house for design subdicing is we need to know what is the substrate material and its thickness, the reticle map, like how are you floor planning multiple designs on the given die, the critical dimensions of each individual die, like the area covered by seal ring and the scribe lanes. We'll need to know these things. The scribe lane is generally dependent on the material type and the thickness. Another thing that we can request from the foundry is MPW wafer. Generally, when you send the chips for fabrication, you receive the designs back in die form, but sometimes it is easier to process a complete wafer than processing small, tiny dies. So the wafer form of MPW designs is available from foundries. We generally do it for TSMCs and global foundries. So in the wafer form, when we are talking about an MPW wafer, there are multiple designs from multiple design groups on a single wafer. So what the foundry will do when we request them a wafer form of your designs, the foundry will laser scribe all the other designs on that given wafer and erase the other customer patterns. The only patterns that will be in working condition will be the active project, like your project, and then the foundry will send us this wafer back. So we can have, depending on the technology node and the foundry, we can request like 8-inch or 12-inch wafer form of your design projects directly from the foundries. So, and this is something that we can, this is something which is like cheaper than doing an engineering wafer, and it's still good for prototyping design.